So it all started when you think about constructing a high-rise building, which is ties to SDG9, resilient infrastructure goals. It is giving one huge headache for civil engineers to design the water supply distribution throughout the levels. Classic textbook like white fluid mechanics and mindset fundamental of fluid mechanics state that the velocity and the pressure of the fluid is intertwined. Therefore, standard design code like BSEN806 and MS1390 state that we as engineer must strategically design the pipe in order to control it. And to solve this, a Venturi meter is a great model example to simulate this real-world infrastructure.
Now let's go through our objective. Our first objective is to evaluate the validity of Bernoulli's equation across three changing design parameters: flow rate, manometer tubes diameter, and volume of water collected. Next, to provide practical design solution for real-world water distribution.
This slide explains the theory behind our experiment, which is Bernoulli's equation. It states that the total energy of a flowing fluid remains constant and consists of pressure head, velocity head, and elevation head. A key concept is the fluid velocity and pressure are intertwined. When the fluid flows through a narrower section of the pipe, its velocity increases while its pressure decreases. Conversely, when the velocity decreases, the pressure increases. In this experiment, we verify this relationship by measuring the pressure at different points along the tempered pipe.
Okay, so before we start our experiment, we need to know the apparatus of the experiment. Okay, let's go. Okay, first, we have ruler. This apparatus we use to measure the diameter of the Bernoulli's apparatus and diameter of this H tube. So as we know, this already have diameter of this H tube and the Bernoulli's apparatus. Okay, so next, we have stopwatch. This is to measure the time of the flow rate. Next, we have Bernoulli's apparatus. Okay, next we have hydraulic bench. And next we have stopper. Okay, lastly, we have on and off switch for the hydraulic bench. Okay, that's all.
First, switch on the hydraulic bench apparatus. Next, open the control valve slowly to allow water to flow through the Bernoulli's test section. Adjust the flow rate until the desired water level is achieved and wait until the flow becomes steady. Observe the water levels in each piezometer tube and ensure there are no trapped air bubbles. Next, close the pole stopper to measure a discharge by collecting water in the measuring tank. By using a stopwatch, record the collection time based on the volume required and calculate the actual flow rate. Finally, record the pressure head at each tapping point and repeat the procedure for different flow rates.
Next, for the sample calculation, we will use the data from test 1. First, the cross-sectional error is calculated using the formula pi r square. The calculated error is 4.9087 times 10 to the power of negative 4 meters squared. Next, the velocity is determined using the equation v equal to q over a, which gives a velocity of 0.2324 meter per second. After that, the velocity head is calculated using the formula v square over 2g. The result obtained is 2.7528 times 10 power of negative 3 meter. Finally, the total head is calculated by adding the velocity head to the manometer head reading from the Bernoulli's apparatus. The total head obtained is 0.2478 meter. The figure below shows how the principal Bernoulli works. So these are all the tests that we conducted, namely test 1, test 2 and test 3. The table shows all the results obtained from the calculation. These results were calculated using the same procedure as demonstrated in the sample calculation.
This experiment directly advances the UN Sustainable Development Goal 9, which focuses on industry, innovation and infrastructure. Because the fluid transportation is the absolute backbone of the modern industrial networks, by applying the Bernoulli's theorem allows engineers to design a piping networks that is resilient and energy efficient, that significantly reduces the resource and the power required. In conclusion, our analyzed data spanning collected water volumes from 0.005 to 0.015 cubic meters and flow rates from 0.1141 down to 0.0133 times to the 10 to the power of negative 3 cubic meters per second successfully achieved our objective of proving the Bernoulli's theorem by proving that the fluid pressure decreases as the velocity increases. through the pipe constriction, we have effectively solved our core engineering problem by providing a practical design solution to accurately predict and control the behavior of the flow for the real-world water distribution.